we have a very exciting talk, which is one you specifically selected by voting for the best poster. So Maryam is going to present her work. She's a master's student at Imperial College, and this is her master thesis work, right?
Yes.
So this is even more impressive that her poster was selected as one of the best in this summer school. So I'm really looking forward to hearing what she's doing and what she's planning to do with this work in the future. So first, I want to give you the official Best Poster Award.
Thank you.
The floor is yours.
Thank you so much, Lesia, Jalal, and everyone who worked to organize this great summer school. And thank you so much for giving me this opportunity as a master's student to participate. And yeah, so I'm going to be talking to you about my master's project, which is a work in progress, and the title is AI-based electricity markets. So in the past few days, I'm sure you've heard about electricity markets a couple of times, but to give you just a short overview, the goal of the electricity market is to solve the resource allocation problem, set prices, and serve as a central mechanism for stakeholder coordination and investment signaling. So they've been around for 40 years, and they've been seen as a success in deregulating energy systems. But I believe that they're being increasingly challenged today, and arguably it's time to rethink electricity markets. So the first point I want to make is about decentralization. So traditionally, electricity market is top-down. We have the big producers on the top, the transmission distribution in the middle, and the consumers at the bottom. But as you can see, we're going towards a more decentralized market, and we need to have that in mind when rethinking the fundamentals of electricity market. And as we go from this traditional pooling system to the connected communities and ideas of a peer-to-peer market, then we're going to have too many assets and too many agents in this future electricity market framework that we need to take into account for. And what if instead of spending a few hours every time we want to clear the market, we can learn the task once at a high cost, but then clear the market near instantaneously? So that's where AI comes in as an enabler in this project. AI has recently revolutionized weather forecasting based on similar paradigms. So what if it can do the same for electricity markets? So adding AI in electricity markets would allow for this change in paradigm, and then being able to do this market clearing more often with higher granularity, possibly for time and even space. And then it could potentially allow for accommodating more fairness constraints and adding contextual information in the market clearing from weather, system states, history, etc. So the problem formulation I'm looking at in my project is the simplest version of a market clearing, which is just solving this linear program. The primal variables of the solution would be the resource allocation, and the dual variables would give the pricing. So as you can see, in this setup, we'll just have the suppliers and the consumers put in bids for the quantity and the price they want. And what comes out of the market clearing algorithm would be the scheduled quantities and the uniform market clearing price. And you can see the linear program formulation. So the objective function I'm taking is the maximizing social welfare, which is the sum of consumer surplus and the producer surplus. And then the constraints are just the power balance constraints and the supply and demand bounds. The methodology I'm using is based around the idea that the solution of a linear program is the fixed point of a dynamical system, and we can learn this. So it's inspired by these papers that they introduce this idea of going from a linear program and deriving the ODE system and learning that ODE system dynamics. So just show you a bit more in detail. You can reformulate the LP problem in this format and then derive the KKT conditions. And then you can look at the papers for the maths derivations, but we can just go directly to the corresponding ordinary differential equation system from this KKT conditions. And what happens is that we can learn that. So neural networks can learn regression models, but they can also learn dynamical systems based on local derivatives. So what happens is that we sample through the trajectories and try to learn that. So this process can be done for a single LP, or it can also be done for multiple LPs, but we just need to sample over the parameters as well. And for the market clearing problem here, the parameters then would be the cost parameters of the agents, the constraints of the agents, and the supply and demand quantities. So lastly, the third step would be the feasibility restoration. So this simple neural network method that I'm using doesn't guarantee the feasibility of the outcome, but obviously electricity system is a critical national infrastructure, so the solutions need to make sure it's safe and reliable. So I'm currently only using a heuristic method. It's just a very cheap post-processing method to deal with this. But next steps would be looking into including physics-informed losses and implicit layers and just other better ways of dealing with this feasibility restoration. So I want to show you the first case study, which is just solving a basic linear program. You can see the problem setup is just 6 variables and a bunch of constraints. And on the other side, you can see the dynamics and the trajectories of the primal variables and the dual variables as the model is learning them. And we are evaluating the final solution at this final t value, which I've just assumed to be 100 at this point. This is a parameter that needs to be tuned, so yeah. So you can see here that the dynamics for some of these variables are smoother than the other ones, and they're like more predictable, but overall, this kind of shows that this idea can work. The second case study I want to talk about is the toy model electricity market. And it's just going a step further from that simple LP and learning over multiple LP problems and bringing these input variable samples. So I'm just assuming here we have very simple electricity market of just 3 producers and 3 consumers. And then the parameter is sampled from the simple range of 0 to 1. I'm learning over 100,000 samples and then testing this over 5,000 samples. Here I'm going to show you the results from just one instance of the testing set. You can see that I'm comparing the original LP solution I've just solved with Awardee to the solution from my neural network, and then the later stage of having the feasibility restoration. So as you can see in the direct solution from my neural network, it's not really feasible. For example, production 3 is negative. That cannot happen. We have more consumption. The total consumption is more than the total production. That cannot happen. So this is solved in the feasibility restoration. But then the output isn't really optimal. So you can compare the social welfare of the feasible solution is less than the optimal LP solution. So it's learning, but it's not fully there yet. And another thing to note is about the pricing problem. So the price that I found through my neural network method is higher than the LP solution. And what that means is that the producers are going to get better value, but then it's more unfair for the consumers because they have to pay a higher price. And kind of going to the more general results from the full testing set, these are some metrics I've evaluated. You can see we're learning both the resource allocation and pricing based on the fluctuations of the LPs. However, it's much easier to predict the resource allocation as compared to the dual variables, which gives us the price. And these discrepancies kind of are possibly due to the sampling problems and the method itself. So further hyperparameter tuning and just adjusting could improve the solutions I'm presenting right now. And lastly, I just wanted to talk about some of the challenges ahead. So first one is about scalability. So market clearing is much more complex than what I just explained. So it needs much more work in terms of generalizing it to more complex optimization problems. And then the other ones would be finding better feasibility restoration methods and improving accuracy of the results. Yeah, thank you for listening.
Okay, yeah, thanks a lot. So who would like to ask some questions? Okay, maybe.
Hello, thank you very much for the very interesting talk. I think this is a very interesting topic. Just to make sure I understand like the whole notion of this correctly, could you go back to, I think it was case study 1, you saw a graph where you saw like how the solution of the neural network converges. Just to be sure, so is this supposed to be understood as at a certain point the neural network will converge into the solution to the original problem? Is that how the notion is with this sort of neural network that you're trying to train on? Or what is...
Okay. So what happens is that I'm turning the LP problem into an ODE system. So this is the dynamical system that will reach the equilibrium. So I'm just having that, for example, T100 as the point I'm assuming it has reached equilibrium and I want to evaluate it. So the neural network tries to learn this trajectory of the ODE system and evaluate it based on that.
Nice. So every time you solve an instance of this LP, then you have this convergence, or?
Yes, that's the idea specifically for the single LP problem.
Okay, nice. Any other? Yeah.
Thank you very much as well from my side. I also have a question regarding how do you determine the price here? Because in an LP, it's always, you know that from the nodal balance, dual variable. How do you do that here?
So here the parameters that I'm getting from this ODE system has both like the X and the U values, which are the primal and dual variables. So I'm learning both of them at the same time. So the number of my variables is the number of primal variables plus the dual variable. So I'm learning everything at the same time as just extra parameters of my neural network.
Maybe just a quick follow-up question. So could it be then that the price that you determine here is decoupled then a bit from the primal variables?
The reason it's assuming that it is coupled is because of the formulation here that it's coming from the KKT conditions. So the dual variables are from there and they should be kind of correlated.
Okay, yeah, thank you.
Anybody else? Up here.
But maybe a stupid question, but why do we convert it into an ODE system and not try first? I don't know. Just learn the solution of the linear program. Is there some studies about that?
The main goal I had with choosing this methodology from this paper was solving the resource allocation, the pricing at the same time. So advantage of this method was that I can get those two correlated from the original equations. That's the main reason I've chosen this.
And what if we just learn the KKTs instead? Or just what are your views on that? Or
Yeah, I haven't explored that, but that's a good idea I can think about for later.
thanks.
Yes. I saw him first.
You explained in the beginning that you then only have to solve this neural network once, but don't your conditions change every day because you have different bits coming in, and so don't you have to retrain every day?
No, so when I'm training for multiple LPs, I'm not just sampling for the time trajectories, I'm also sampling to learn over multiple LP problems. So I sample parameters for the cost, the agents, and the quantities as well. So when I have this toy model, I'm kind of generalize the model to solve any LP of this specific size that can be for any. Yeah, so then an assumption I'm making is that the number of agents for now is just constant. So here I took 3.
Okay.
Yes.
Thank you very much. I really think it's a very interesting topic. In the end, since the neural network have the tendency of outputting higher price, and this could be counterintuitive, saying that you are optimizing social welfare, maybe you were planning to explore this to also link it to have part of the objective of the outcome to be also system security, or I'm assuming that this your A matrix is considering the PTDF of the, in the system, so like such that you would have as an output something linking not just price, but also kind of saying, okay, we pick this price because it not only guarantees social welfare, but it's the best for the system, something like this. Is this something you consider?
Yeah, so for now, the pricing, that can be fine-tuned further to improve it. But in terms of next steps would obviously be making the problem more complex and adding those extra parameters. I think that's ideas I could explore further in the next stages.
You could have raised your hand when I was up there.
What is the training data set for your neural? You are trying to solve this primal ascent dual descent using the neural network, and so what is the training data set, and how do the parameters impact the how is the ODE solved using the neural net?
The training sample I'm using is just, I've assumed that the bits are in between 0 and 1, and for each instant, I just randomly sample to create a new instant. So that's how I've created the training data set.
So it's for this specific market configuration?
Yes.
And so if you have to learn for different market configurations, you have to retrain your model? Or
Yeah,
if you want
that's
to
the
have a bigger
idea,
market?
yeah.
Okay.
But then also that I've assumed 0 to 1, so that even if I have bigger problems, I can just scale them down and scale them up. So ideally, it would still work even if the numbers are out of this range.
Okay.
Yeah, thanks. So as you say, as I understand, like the strength is that when the complexity increases, this becomes valuable, right? So I was just wondering, like, how easy the methodology is to transfer to other more complicated formulations, just say like mixed integer or like nodal market clearing and stuff like that.
Yeah, that's a challenge definitely I have ahead of me. I haven't really explored that yet, but it is in the process of the next stages for me.
Nobody else up here, right? Okay. Was there somebody? Oh, Jalal? No? Oh, Richard.
Instead of taking on such a gargantuan task, you may want to think about using AI as a starting point for mixed integer programming, the advanced start, because if it can choose the generators to start up correctly, it's almost all the way there.
Yeah, thanks. So I have one question, but we talked a little bit about it when you were presenting your poster. You had one point that was to extend this to look more at prosumers or consumers with complex preferences and use this approach to represent this. So do you have some thoughts on, I know you haven't started your PhD, but do you have some thoughts on how you could do this and how this method then would be valuable for this application?
Yeah, so the idea is to have this AI as a core and then be able to add more things on top of it to do more cool things I couldn't do before. And one of those is the preferences and the prosumers kind of in the market. I haven't really explored exactly what these could be yet, but I'm very interested in exploring those further.
Cool. Yeah, I look forward to seeing what you do in that topic. I think it's very interesting. Anybody? No? Okay. Then, yeah, just thank you again for a very interesting poster and presentation. Thank you. Thank you.